Let's start lecture 15 and let's continue topic building construction surveys and talk about 3D laser scanning. How does it work? 3D laser scanning emits millions of laser lights and by timing their return can accurately and precisely calculate their 3D locations to produce multiple high-speed scans brought together into one system. It works by digitally capturing the dimensions and spatial relationships of objects using the reflection of a laser light. The technology has a wide array of job site applications, including pre-construction as-built, building information modeling, virtual design construction, quality control during construction, comparing design intent to as-built conditions. When objects or exciting site conditions are scanned, millions of data points are recorded, invisible to the human eye. And the result is an accurate depiction of the scanned site or object. This accurate depiction is called a point cloud. Point cloud data goes into a common reference system where it's merged into a complete model. This process is called alignment or registration, and dozens of scans can quickly be stitched together. The 3D CAD model created from the point cloud can then aid in extending BIM workflow. And why would you need it? 3D laser scanning is quickly becoming the norm in the AEC industry. In fact, technology is advancing much faster than the industry itself. According to KPMG Global Construction Survey from 2016, the industry is yet to fully embrace technology, and just over 20% of respondents said they are changing their business models to accommodate this rapid growth. In addition, data volume is rising quickly, causing most executives and project owners to struggle to make sense of the information. The result is an industry far behind others in adopting the latest tech. The bright side? A small group of contractors now have the advantage. Since much of the industry has struggled to adopt even the most basic technology, firms that do are catapulted well above their competition. With the ability to capture data at 1 million points per second, with a scan time of only 3 minutes, adopting 3D laser tech is a great first step. Also, the benefits go beyond just 3. The video below will give you a good idea of how scanning technology can catapult your firm, and in the next time when you will work somewhere, you well above the competition. Key benefits of 3D laser scanning. First, speed, accuracy, and consistency. 3D laser scanning enables a fast and accurate means of collecting millions of measurable data points in seconds to provide pinpoint accuracy every time. Valuable data for design. This is a second. Data sets are dimensionally accurate, measurable, and shareable, so you can eliminate any guesswork back at the office. And third, works on retrofits and new builds. For detailed map installations, you need a high level of accuracy. If your project is complex, involves retrofits, or requires refurbishment, you can capture precise data over the full measurement range. And for example, you can use a Trimble, a leading provider of products and services that connect the physical and digital worlds. Laser scanning works quite similar to traditional survey instruments, in that it is measuring a horizontal and vertical angle combined with a slope distance. But what it's doing is revolving a laser very rapidly through a vertical and horizontal arc, while using those laser pulses to measure the distance. That result in millions of points per second. Here you can see a million points. This is a real building, and this is a million points, cloud of million points per second being stored in the onboard computer. One of the major benefits of using a laser scanner is it greatly reduces project liability. The way it does that is there are lesser unknowns about the project because whether or not something is represented in the CAD deliverable or the survey data, the engineer or the technician can actually take the points cloud, look at the enter site, and identify other areas of interest. It's a much more holistic approach to analyzing the data in an environment. So, if we have girders or bolt patterns or curve and gutter, all of these different things are represented on laser scan, which we are usually used to going out and surveying the site for a civil engineer and then later for a structural engineer, whereas we have one data set with both deliverables waiting to be extracted from it. Whenever you can take data and you don't turn it into 2D and then back into 3D and then back into 2D to actually build it. What laser scanning allows you to do is take a 3D environment, represent it in 3D and design in 3D. That eliminates all those conversion steps and saves project time and money. That's very important and useful, of course. So here you can see an algorithm, a scheme, how to scan to Revit. So point clouds to beam for building workflow. The first one, this is a Faro scanner, and then you receive a Faro scene and registered point cloud. Then you can send it to edgewise or point sense that include data extraction, data modification and creation, and then send to Revit or any project of building information modeling, and then you design and make drawings and then analyze all this information 3D and 2D models. What is uses of workflow focuses? Increases accuracy of models, leverage automated process, reduce manual modeling, reduce as-built modeling times. So here you can see point clouds to beam after scanning. And then you can send model from point clouds to beam and perform some elements of the building. If you have some point clouds, million point clouds. And then you can make a 3D model in Revit. And now let's to see a laser scanning for as-built drawings. How are you doing your as-built measurements today?
If you're like most people, you're probably doing a lot of hand measuring, which is very tedious and time-consuming. Then, at the end of the day, what are you left with? Inaccurate and incomplete data. 3D laser scanning changes all of that. With 3D laser scanning, we can create a highly accurate three-dimensional model of the complete interior and exterior of this building that we can then use inside of our CAD application to do our renovation. We start by positioning our 3D laser scanner on the site to be captured. Now we will run the scanner to capture the first scan of the building. To capture the scan data, the scanner uses a laser that is bounced off of a spinning mirror to measure the distance to the point the laser hits to an accuracy of 2 millimeters. As the mirror spins vertically, the scanner captures a column of data, and as the scanner rotates horizontally, it captures a complete 360-degree dome of points. The scanner can capture up to 976,000 points per second, and the final collection of points we call a point cloud. Next, we'll move the laser scanner to the next scan location. Since the scanner can only capture what is within its line of sight, we typically move the scanner around both the inside and the outside of the building that is being scanned. to fill in the missing areas and create a complete point cloud. Before capturing the next scan, we will position targets in the direction we are moving the scanner to tie this scan location to the next. These targets will be used to automatically combine the multiple scans into a single dataset of the complete as-built condition. Now we are in Ferrocene, the software that comes with the scanner and is used to process the scans. Here we are looking at the data captured at one of the scan locations. This is a sort of panoramic image, looking from the point of view of the scanner. We can also look at the scan in a planar view, which takes the sphere of data and unrolls it to look at the entire scan at once. Even though this looks like a photograph, every pixel in this image is a three-dimensional point captured by the laser scanner that we can use to take measurements. When measuring from the floor to the ceiling, the dimension is broken out to give us the true vertical measurement. Now we are no longer looking from the point of view of the scanner, but are looking at the true three-dimensional point cloud of the captured data. As we zoom out, you can see the amount of data that were captured from just a single scan location. After all of the scans have been registered together using the targets that were placed in the field, the complete point cloud can be seen. From here, we can export the point cloud to our downstream applications for use in planning and design. When using any of the Autodesk products, we will bring the point cloud into Autodesk Recap. Recap is a high-performance point cloud visualization engine that is not only a standalone application, but is also built into many of the Autodesk design suites. We can use the Recap application to view and navigate the point cloud. By cutting sections of the data, we can view the model in ways that would otherwise be difficult using data collected with traditional means of as-built surveying and measuring. Here, we are cutting a cross-section to view the floor-to-floor relationships and to determine the distance between the floors. We can get an understanding of the interstitial spaces and the ceiling plenum. Recap can also be used to take measurements and make markups of the point cloud. We can measure a point-to-point distance in 3D, a distance perpendicular to a face, or to the center or edge of a pipe. Now we are in Autodesk Revit, where we can attach the point cloud to a project as a link. We're going to start by creating a section view to align the point cloud data with the level datum lines that we established for the first floor and second floor of the building. This will allow us to create accurate floor plans for modeling the building to create a complete building information model. Looking at the floor plan view, we see the plan section is cut all the way to the floor level, so we can see the floor's materials and finishes. Here, we're going to adjust the view range to clip the view just above the floor to create a floor plan. And now we're going to do the same for the second level. The elevation views created from the point cloud are true orthographic representations of the building. This is difficult to capture with traditional photography. By working in context of the true as-built point cloud data, we can plan renovations and adaptive reuse projects and coordinate construction projects. With only a small amount of effort, we can create a rich and precise building information model that accurately represents the actual building conditions. Switching now to another project, let's look at an example of how we can use Autodesk Revit to work in context of the point cloud data to do an architectural renovation study. This is a laser scan taken in the lobby of a historic 19th century hotel. Here, we're looking at a 3D view of the model in Revit, and we're going to clip the roof off of the building to look at the interior of the space. Here on the floor plan, we're going to take a section through the hallway to look at the area where we will be doing the renovation. Creating a perspective view allows us to get a sense of the space and the design requirements. We can move and look around the space in real time. Now, let's do a renovation to the space. We're going to add a new wall with a door here between these columns. Notice that we can snap and track from the point cloud to make drafting easier. Looking back at the 3D view, we get the proposed new wall in the context of the existing space. Back in the section view, we see the wall and how it relates to the space vertically. In the perspective view, we see the proposed new wall as it would appear in the final renovation, and we can move around to explore the area and get an idea of how the proposed design will affect the existing space. Now, let's change the door and see how that changes the look and feel of the space. Call DLT Solutions today to find out.
And the next topic and next video, what is the 3D laser survey and design services? So, 3D laser scanning surveys are continuing to drive innovation in the way in which we acquire and record measurement data from physical environments such as sites, buildings, or plant facilities. Assessing very accurate measurement data along with high definition 3D imagery, which can apply it throughout your design, delivery, and competition processes. So, it was a last lecture. I wish you good luck and good marks. Understand, you must understand that for a civil engineer there is no such thing as a little mistake. Bye.